All right, good morning, everyone. It's a true pleasure to introduce our esteemed speaker today, Mr. Michael Wang. Let me begin with introducing myself. I am Dr. Abdullah Mudbil. I'm the director of the KACST-UCSB Center of Excellence that works on development of next generation photonics and electronics, and that include UVLED. UVLED, as will Mr. Wang present, is very instrumental for important technologies like water disinfection, air disinfection, and so on. Our speaker today, Mr. Wang, holds a Bachelor of Science from UC Berkeley, and in 2019, he joined the engineering school at UC Santa Barbara to pursue his PhD in material science. And since then, he has been working full-time, working hard on the development of UVLED, and luckily, his innovative and hard work has led to multiple breakthroughs, including the recent world record in UVB LED efficiency. KACST has a long history with UVLED research. It started funding the research in 2016. Two KACST researchers had PhDs in the development of UVLED, myself and Dr. Burhan Saifuddin. And so we continue to be invested on this research. Today, we have the distinct honor of hearing from someone who just had achieved a remarkable milestone in this technology, publishing a world record result in UVB LED research. So please join me in warmly welcoming soon to be Dr. Michael Wang. Dr. Wang, please.
Thanks for the great introduction, Abdullah. So today I'll be talking about my recent results in UVB LEDs, resulting in a world record efficiency. So a little bit about me. I'm a graduate student now, soon to be, hopefully, PhD. I'll be defending in just 2 weeks. I visited Saudi KACST in January 2024, and helped out with teaching people there to fabricate UV LEDs. So I brought some epi from our reactor, and we were able to successfully fabricate devices in the clean room there at KACST. So I've been here at UCSB for 5.5 years, almost 6. And after I graduate, I'll be sticking around as a postdoc and continuing to work on UV LEDs. So here's the outline for today's talk. Bit of introduction of our work. So this is a timeline of published UV LED results from our group. So the first point is from Dr. Burhan Saifuddin. Back in 2019, and we've quickly surpassed commercial UV LEDs, which are typically around 3 to 5% wall plug efficiency. So on the left with the black, you can see external quantum efficiency, which is efficiency in terms of number of electrons injected into the device versus number of photons that you get out, and wall plug efficiency, which is just energy in versus energy out. So in 2020, we matched commercial UV LEDs, and after that, we quickly surpassed them. And recent results here, we've achieved 20% EQE and around 18% wall plug efficiency. So just a quick comparison to different research groups around the world. So commercial LEDs are down here, just consistently have not been improving that much. We actually did recently a survey of commercial samples, and they're still around here. So in 2023, I published 8.6% wall plug efficiency, UVB LEDs at 285 nanometers, and recently I published UVB LEDs in around 300 and 310, around 15 to 18% wall plug. These estimates are for the epi that we've grown but not processed yet and are currently working on processing. But of course, we will definitely follow up on publications whenever we get these fully processed and packaged and measured. So just to compare to the current technology of mercury vapor lamps typically are around 20% wall plug at UVC wavelengths for disinfection. And at UVB wavelengths, they are less than that. So basically, best case scenario for mercury vapor lamps, which are the incumbent technology, is about 20%. So now with our recent publication, we are on the order of the same efficiency compared to mercury vapor. This is external quantum efficiency compared to the rest of the world. So the 2023 publication is around here. 2025 publication is around here. And the estimates from our current epi, our current material, is around here, and commercial is definitely around here. So a bit of background, the main use of UV light is, and the biggest use is UV disinfection. So this is not new technology. This has been around for quite a bit of time, almost 100 years. In the 1930s, people discovered that UV light works as a disinfectant. And in 1903, there was actually a Nobel Prize awarded for that. In 1930s, it was already widespread in hospitals and as mercury vapor lamps. And over time, these mercury vapor lamps have been more and more widespread, used not just in hospitals, but in wastewater treatment plants, in water purification, and with recent technologies of UVLEDs, which are very small. They can be used in point of use cases where we can have, for example, household water disinfection. And how it works is it triggers a reaction in DNA called pyrimidine dimerization, and basically destroys the DNA of viruses or RNA, DNA, bacteria. And as you can see over here with incubation of before and after sterilization by these UVLEDs, there's a clear drop off in germicidal or bacterial presence. So UVLEDs are the 21st century solution to creating UV light. Mercury vapor lamps, although pretty efficient, are pretty big, bulky. They require a ballast and high voltage, since you need voltage to create high voltage to create this electrical arc to emit light from ionized mercury vapor. And then this is obviously not ideal for point of use cases or to design apparatus around disinfecting water because of the bulkiness of these light sources. So with modern UVLEDs, which are very small and easily controllable, fast on off, highly efficient, and long lifetime, very reliable, it is only a matter of time before UVLEDs will replace mercury vapor lamps. And more background, so this is the ultraviolet spectrum between 100 nanometers to 400. So germicidal wavelengths typically are between 240 all the way, or 220 all the way out to 310. There is some germicidal effectiveness, and the peak of germicidal effectiveness is around 265 nanometers right here. And as you can see, 300 and 310 definitely is still germicidal, but it is pushing the boundaries a little bit. And we are definitely working on moving the peaks of emission for our recent world record devices into the germicidal region. We did previously publish 285 nanometers at 10%, and we will definitely surpass that by a significant amount. I also should mention for UVLED for germicidal, the shorter wavelength you go, the harder it is, because the higher in aluminum of material you need, and the harder the material growth. So typically for germicidal UVLEDs, we target around 270 to 285 nanometers emission. So UVB, which is from 280 to 315 nanometers, does have its own uses. So it is not just germicidal. UVLED does not just focus on germicidal applications. For example, there's the biggest use of UVB light, which is in treatment of skin diseases such as psoriasis, vitiligo, eczema, vitamin D deficiency. UVB light from the sun is actually what promotes the synthesis of vitamin D in our systems. So another main use is photochemistry in the industrial applications. So in photochemistry, for example, one example reaction that can utilize UVB is 300 nanometer light used in 2+2 photocycle addition. It also is used, I believe, in cubane, in the synthesis of cubane compounds. So those are some uses. So to start, I will give some background on our UVLED work from Dr. Burhan Saifuddin and Dr. Abdullah Al-Megbel. So initially, we chose silicon carbide as a substrate, so as a template for our material growth. This was in 2019, and right now we're on sapphire. But why silicon carbide back in the day? So the reason is that in 2019, aluminum nitride on sapphire was very defective. So TDD is a measure of the defect density, threading dislocation density. And aluminum nitride on sapphire back in 2019 and earlier was commercially like in the high 10 to the 9 to 10 to the 10. And it was very difficult to get good samples of aluminum nitride on sapphire, mostly due to the large lattice mismatch of approximately 13% between the aluminum nitride and sapphire. Over here on the low side, which you would prefer in terms of defect density, bulk aluminum nitride or lateral overgrowth methods is used to achieve this, but both of these are extremely expensive even now, and are not commercially viable technologies at this, even now in 2025, and much less in 2019. So our initial work in our group was on aluminum nitride on silicon carbide, because the lattice mismatch between aluminum nitride and silicon carbide is less than 1%. So material is much easier to grow at much higher quality. And another added bonus is that even though silicon carbide is absorbing to ultraviolet light, it is possible to remove the silicon carbide after the growth of aluminum nitride and our UVLED material on top with a flip chip process that we'll go into quickly after this. And once the silicon carbide is removed, you can roughen the backside surface of the aluminum nitride to allow the emitted light to escape from the device, light extraction, relatively easily compared to even aluminum nitride and sapphire material. So light extraction is the main barrier to high efficiency UVLEDs today, because of total internal reflection in the interface between aluminum nitride and sapphire, or aluminum nitride and silicon if you manage to grow it on silicon. But basically, total internal reflection is what occurs at those interfaces, and unless you find a way to remove the substrate, it is very difficult to extract all the emitted light, and a lot of light gets getting absorbed in the device. With silicon carbide and the flip chip process, we can remove the silicon carbide through a dry etch, which is not as easily done with sapphire, and then that would allow for the light to escape, and there would be no aluminum nitride to substrate interface left for total internal reflection. So that was the main selling point behind our initial ideas. And in growing this aluminum nitride on silicon carbide, we discovered, and also growing UVLEDs on this aluminum nitride, we discovered many things. This is the work of Dr. Abdullah Al-Meghbul. He published this in 2021. This is the n-type material. So in the diode with the n-type material, the n-type material should be very conductive because, especially for nitrides, the p-type material is extremely not conductive compared to, for example, p-type silicon, conventional semiconductors, p-type gallium arsenide. So for nitride materials, p-type gallium nitride and p-type aluminum gallium nitride are extremely non-conductive. The n-type needs to be extremely conductive to spread the current well throughout the entire device. We discovered early on, Dr. Abdullah Al-Meghbul discovered that if we decrease the 5:3 ratio, we can get rid of a knee effect that we observe in our material. So this knee effect is basically what happens when you try to dope AlGaN, especially high aluminum AlGaN, around 65% aluminum, typically used for UVLEDs because of its transparency to UV light. What happens is, as you flow more and more silicon, the resistance of the material drops off, as you would expect, but then quickly shoots back up due to compensating behavior. What Dr. Abdullah Meghbul discovered was that if you decrease the 5:3 ratio all the way down to an extreme like 10, this knee behavior widens dramatically, so the conductivity drops off, but then stays very low for a wide range of silicon flow. And the same trend can be observed in the mobility and carrier concentration. So in the carrier concentration, the conductivity would, with normal high 5:3 ratios, drop off extremely quickly with more silicon flow, but with ultra low 5:3 ratios, this carrier concentration would stay flat with more silicon flow. So this 5:3 ratio is basically, for those who don't know, is the ratio between the flow of group 5 element to the group 3 element. So group 5 is nitrogen, so ammonia, to group 3, which is trimethyl gallium and trimethyl aluminum. Another thing we discovered was that we were growing too hot in temperature, and lowering the temperature helps with the conductivity as well. So with this work, we were able to achieve easily and consistently 4 milliohm centimeters of resistivity at 65% aluminum, which is among some of the best resistivity in the world, and 7 times 10 to the minus 5 ohm centimeter squared contact resistivity, which is also some of the best in the world, and a sheet resistance of 90 ohm per square, which is extremely good for this high aluminum in AlGaN. So going on off of that, we worked on the UVLED epi on silicon carbide, and this is the main idea of using silicon carbide, is that we can remove the substrate to extract the light from the device. So we first grow our device in MOCVD, so this is silicon carbide, this is n-type material, n-type AlGaN, this is our quantum wells, this is the p-type, and this is a p-type gallium nitride for hole injection, because our p-type aluminum gallium nitride is very resistive. So the process involves first etching down to the n-type, putting contacts on both of them, depositing metal, attaching a submount through flip chip bonding. So this is indium gold bonding. So gold, indium gold, and then mechanical pressure and heat, and that bonds the materials. And you can flip this over and then dry etch off the silicon carbide substrate and roughen the backside of the aluminum nitride. And this results in a light extraction efficiency of greater than 30%, which is actually greater than what we have now with the Sapphire world record epi. So this is definitely very promising technology. And if we could have our quantum wells that we grow now, or on with the world record device on this, and have this kind of light extraction, then we would destroy the current world record that I just published. And this work is was headed by Dr. Burhan Saifuddin. So this is a comparison between the efficiency of the UVLED just on the silicon carbide versus the thin film flip chip UVLED device. So you can see that getting rid of the substrate and roughening the backside of aluminum nitride increases the light extracted from the device by a factor of 20, which is incredible. I wish I had this kind of light extraction on my current devices, but we will continue to work on that. So this is the epitaxial film stack. So because silicon carbide and aluminum nitride are closer in lattice constant, you can grow much thicker material and still not crack the material. So this is a diagram of the flip chip process, bonding, and then roughening, or getting rid of the silicon carbide substrate, and then roughening the aluminum nitride backside. All right, so going on to the current, my work that I headed on UVLEDs on Sapphire. So why, I just said that UVLEDs it was a better choice to grow it on silicon carbide than Sapphire. So why did we switch back to Sapphire? So in 2019, it was better to grow UVLEDs on silicon carbide because of commercial aluminum nitride on Sapphire, and also just homegrown aluminum nitride on Sapphire being extremely defective. So our silicon carbide work is one order in magnitude better than the best aluminum nitride on Sapphire in 2019, and 2 orders of magnitude better than the average aluminum nitride on Sapphire in 2019. However, in 2021, there was a big breakthrough in aluminum nitride on Sapphire templates with high temperature face-to-face annealing. What is done is aluminum nitride is first deposited on Sapphire through, for example, sputtering, MOCVD, HVP, all these different processes, it doesn't really matter, and then annealed at around 1700 degrees Celsius. And that decreases the defect density by basically an order of magnitude. So our silicon carbide aluminum nitride is still slightly better, but it is much more closer to the commercial aluminum nitride than in 2019. So the benefits are that this aluminum nitride on Sapphire is highly consistent and it's inexpensive in terms of purchasing from industrial suppliers. It is a transparent substrate, whereas silicon carbide is not transparent. So it enables rapid LED optimization in growth through quick test, which is a process where you deposit indium contacts through a mechanical process. So first, you take the epi and then you use a diamond tip pen and you scribe one corner, and then you use a soldering iron to put down indium. And by scribing that corner, you expose the bottom end conductive N-type material so that you create a pathway through the bottom, and then you put on regularly sized indium dots on the top side, which give you the p-type contacts. So this is a very quick process. There is no fabrication involved. You can do it by hand very quickly, And because of that, it allowed for very, very rapid LED optimization. Another benefit is that aluminum nitride actually has a higher than previously estimated. So this dark blue line was what people were talking about in terms of absolute maximum in IQE, theoretically, with the amount of defects in the material. So IQE is internal quantum efficiency. But what we discovered is that aluminum nitride and high aluminum AlGaN is more tolerant to these defects than we previously thought, due to this wide band gap of aluminum nitride and AlGaN, which result in very short radiative carrier lifetimes. So the carriers do not have enough time to move to find the defect before they recombine. So this definitely gives a wider range of defect densities that are usable for UV LED devices. A huge downside of aluminum nitride on sapphire, even in today's day, is the decreased light extraction efficiency. So aluminum nitride and sapphire, the interface between the two materials, is a highly reflective interface, and all the light that gets emitted on towards the bottom side of the towards the substrate, a majority of it gets reflected from at that interface and does not leave the device because of total internal reflection. So we started growing with our old silicon carbide recipes on sapphire, and this was what we started with: 500 nanometers of N-type aluminum gallium nitride. After a thin buffer of 85% undoped aluminum gallium nitride on top of aluminum nitride templates. So this silicon carbide we replaced with the sapphire aluminum nitride commercial templates. And then this active region that we started with just standard quantum wells and quantum barriers, and our aluminum gallium nitride p-type material. Early on, we did experiments comparing uniform bulk layers of p-type aluminum gallium nitride and superlattice layers, where we alternate between a low aluminum and a high aluminum material in a short period superlattice. These layers are on the order of 1 nanometer now. And then on top is this p-GaN material. And p-GaN is still used, even though it is not transparent to UV LEDs. Because aluminum gallium nitride, even with short period superlattices to enhance the hole concentration through polarization effects or through graded layers or polarization doping, is still not providing near enough holes for this device to operate well. So we typically have a layer of p-type gallium nitride on top of a p-type aluminum gallium nitride. And this supplies all the holes that are needed for the device. So the initial UV LED results on SSP is single side polish sapphire, aluminum nitride templates. Sorry, my advisor is messaging me. Anyways, so we have morphological issues that we observed. So the difference between aluminum nitride on silicon carbide versus aluminum nitride on sapphire is that the lattice mismatch between aluminum nitride and sapphire is around 13% versus the lattice mismatch of aluminum nitride and silicon carbide is around 1%. So the defect density is definitely still higher than the aluminum nitride on silicon carbide templates that we were growing before. With this high defect density, what occurs is that as you grow thicker and thicker N-type aluminum gallium nitride, you observe a drastic blowing up of the morphology. So at 400 nanometers of N-type aluminum gallium nitride, the N-type aluminum gallium nitride is growing in this almost cauliflower-like morphology with a roughness of around 3 to 5 nanometer RMS. But as you grow thicker and thicker, over here, you see 1600, this is 1600 nanometers of n-AlGaN. And you can see that the roughness just goes off the charts. It results in larger than 100 nanometer tall islands. Sorry, give me 1 second.
Your alarm is going off.
Okay, sorry about that. So it results in larger than 100 nanometer tall islands with these holes in the middle. We can see these look like volcanoes, and this is definitely very detrimental to UV LED devices. You can't grow UV LED devices on this. So in terms of what's going on in the material, so this is reciprocal space mapping of material. So 400 nanometers of n-type aluminum gallium nitride, you can see the aluminum nitride, our interlayer, which we grow on, the buffer layer between the n-type aluminum gallium nitride and aluminum nitride, because our aluminum n-type material is 65% aluminum, and it is too far from the aluminum nitride in terms of composition. So we add this interlayer to smoothen out the 65% material. And as you grow thicker to 800 nanometers, this material actually starts drifting in composition. So all of this is the same growth condition, the exact same flow rates, the exact same temperature. And what happens is the aluminum starts decreasing in the material, and more gallium is incorporated. And additionally, the material is beginning to relax. So at the full 1600 nanometers, we can see 100% relaxation of the n-type aluminum gallium nitride, and over here it's all the way down to 35% aluminum. So what's occurring here is that the threading dislocations in the material, so these are the threading dislocation defects imaged through transmission electron microscopy, are inclining due to the heavy silicon doping that's required to get the very high conductivities that we desire for our devices. So with this inclined dislocation, you can think of this inclined dislocation as a pure thread component, which is vertical, and a misfit component. And the addition of these misfit dislocations throughout the entire material introduces stress in the n-type aluminum gallium nitride. So because of this, when you grow thicker, there is more and more tensile stress incorporated into the n-type aluminum gallium nitride. Now, aluminum gallium nitride is supposed to be in compressive strain on aluminum nitride because aluminum gallium nitride has a larger lattice constant than aluminum nitride, so the atoms are forced to squish down when you grow them on aluminum nitride. However, because of the introduction of these misfit dislocations, components of these inclined threading dislocations, you introduce more and more tensile stress in the material such that you go from compressive stress to neutral to tension, and eventually the material actually cracks. This is a very well done threading TEM image of this crack that forms. And when the material cracks, what happens is you generate a lot of these threading dislocation defects. And even if you overgrow this and recover the morphology and grow to cover this crack up, these defects do not go away that easily. So what happens is at about 800 nanometers thick of n-type AlGaN, which I'll show later, the n-type AlGaN just all of a sudden gets a huge influx of defects, which basically completely destroys the efficiency of the material in terms of optical emission. So these are just for different views of the crack. cross-section views of this crack in transmission electron microscopy. And here's a basic schematic. So what happens is when you start doping this aluminum gallium nitride with silicon, the threading dislocations that were vertical start inclining and adding misfit components. The stress goes from compression to tension, and eventually the material just cracks and then generates a lot of threading dislocations. And this also explains the volcano formations around very thick material, on very thick material. So over here, this is TEM EDS, which measures the composition of the material throughout the entire structure. So you can see here, this is our aluminum nitride, which has no gallium, and then our 85% interlayer, 85% aluminum interlayer. And we start growing our aluminum gallium nitride. And as we grow more and more, the composition starts drifting up because of compositional pooling. So this is when, so how do I explain this? So this can be explained because of when you have a material that is in tensile stress, the lattice constant is bigger, so it more easily fits in the larger gallium atom, and that moves the material to be more gallium rich, which then pushes it further in tension, which then incorporates more gallium. So this effect shows this stress gradient as well implicitly. And then when this gradient stops over here around 800 nanometers thick of n-type AlGaN, this is presumably when the material cracks, and then the gallium, the composition stabilizes. So since the material cracks at around 800 nanometers, I grew an LED with around 800 nanometers of n-type AlGaN, just to show that even if the material still looks fine, the microscopic cracks will destroy all efficiency in the LED. So between the 400 nanometer n-type AlGaN and the 800 nanometer n-type AlGaN, the light emission, so this is light output power, is decreased by more than a factor of 2. And this so this is what occurs when you try to grow too thick. So basically what happens is we can't grow too thick, so we have to grow thin and very conductive. Otherwise, our current spreading is incredibly poor in our UV LEDs. And I also just, around this time, discovered this N-type smoothing layer with alternating layers of 14 nanometers of 60% aluminum and 80% aluminum. Three times of this, so 6 total layers, and with growth pauses between these N-type smoothing layers. So these growth pauses basically are when we turn off the metal organic and just let the ammonia keep on flowing. This actually starts etching back the gallium. So at the high temperatures that we're using for the growth, the gallium desorbs from the surface. And what happens is that it conditions the surface. So this is our typical N-type aluminum gallium nitride surface, which has an RMS roughness of around 3 to 4 nanometers. And with this N-type smoothing layer, what we got was a little bit less overall surface roughness, but a lot less roughness on top of these nanodisk formations. So here's a cross-sectional transmission electron microscope image of our N-type smoothing layer, and you can see that with these pauses, we form these regions that have more aluminum and less gallium, and this definitely helps the morphology to locally smooth out. And that helps the interfaces between the quantum wells and quantum barriers on top. So with these technologies and with optimization of the p-type material, so this is short period superlattice where we have 1 nanometer of low aluminum percentage AlGaN and 1 nanometer of high aluminum percentage p-type AlGaN. And in Dr. Yifan Yao's work in 2022, we found that 80% and 20% aluminum gave us the best efficiency. Theoretically, 95 and 5 would give us more holes, but 80-20 is more transparent because of the 5% aluminum material absorbing too much light. And this results in LEDs with efficiencies of 10% EQE, 10.6, and 8.6% wall plug at 285 nanometers, as shown here. And this was published in 2023. So these results were great, but what happens is that when we tried to grow these LEDs after reactor maintenance and use of the reactor on different projects, we could not reproduce these results easily. And this took quite a significant amount of time to get back our conditions. But what happened was after the reactor maintenance, we could not, so previously our power was around 4 to 5 milliwatts. This is quick test power. So as I explained earlier with the indium contacts. So the best power ever was 5.7 milliwatts at the time, and we could only reproduce 2.3 to 2.6 milliwatts. So of course, this was through a lot of tuning of all of the layers in the LED. And what we ended up figuring out was that because of the substrates being from a commercial supplier and there being variability in the substrates, this 400 nanometers of n-type AlGaN is actually not very consistent and can grow at small amounts of relaxation. So in the published work, we had around 10% relaxation here, and also slight spreading in composition. So main peak is around 65% aluminum, but it definitely does spread down a little bit in aluminum percentage. And what we figured out during this time was that some of the material would grow like this, and some of the RSMs would come out more like this. So even with the 400 nanometers thickness, with different substrates, the stress state would be different with our material. And if the relaxation is significant, that shows that we're drifting towards that uncontrollable compositional drift and morphological degradation, and also cracking. Since our n-type smoothing layer is about 100 nanometers and our quantum wells are about 100 nanometers, if the relaxation is already significant at the end of the n-type aluminum gallium nitride, then at the end of the quantum wells, it will be catastrophic. So what we did was we thinned down our n-AlGaN to 200 nanometers. And that just basically is just avoiding the problem and just giving us more room to grow our quantum wells. Definitely this is sacrificing our current spreading, but because of Dr. Abdullah Al-Megbul's great work on the highly conductive n-type AlGaN, we still have a bit of room to work with in terms of conductivity of the n-type material. So with this new ultra thin n-type AlGaN, this is 180 or 200 around there, with very good conductivity, 4 milliohm centimeters, 5 times 10 to the 19 per cubic centimeter of electrons or carrier concentration, and a mobility around 20 to 30 centimeters squared per volt seconds. We did some initial optimizations, and already it was looking much better than before, and we got 3 milliwatts immediately compared to a lot of large volume of experiments that we were doing with the 400 nanometers and n-AlGaN to reproduce our material, which never yielded anything above 2.6 milliwatts. So this was very promising. So what I did was I tried a lot of different types of quantum wells structures. So this is just a flow of the or you could look at this as the aluminum percentage around a quantum well. So we have, if you remember with the n-type smoothing layer, we had these pauses between the different layers of the n-type smoothing layer. We also had those pauses in the quantum well region. So those created these high aluminum, very thin high aluminum layers between our quantum wells and quantum barriers. So what I did was I tried to reproduce those with different structures and grading of the quantum of from the quantum barrier grading up to that high aluminum, and then grading down to the quantum well, and et cetera, et cetera. And what I found was, in the end, was with these two structures, where we have our quantum barrier, we grade up to this high aluminum layer, grade down immediately, and then grow a quantum well, and then grade up this high aluminum layer, grade down, and grow a quantum barrier, versus another thing where we just immediately change the flows and just don't grade. So these two ended up being the best. This one with the grades ended up working better for thinner quantum wells, and the one without grades ended up working best with thicker quantum wells, because thinner quantum wells emit at shorter wavelengths, and we wanted to target the germicidal wavelengths. We stuck with structure number 10 here. And this structure is basically what is with our recently published world record LEDs. So aluminum nitride templates, and then our standard interlayer, and then 200 nanometers of n-type AlGaN. And we didn't need the n-type smoothing layer because this thinner n-type AlGaN is not as rough as the 400 nanometer material. And on top of this, with our multi-quantum well, we grow this high aluminum layer, grade up to it, and then grade down and grow the quantum well, grade up to the high aluminum, and grade down and grow the quantum barrier. So the total thickness of this quantum barrier and the high aluminum layers is about 9.5 nanometers, and the quantum well is about 1 nanometer. And further optimization and repetition of this structure resulted in quick test records on at different wavelengths of 4.3 at 278, 4.8 at 290, 4.5 at 293, 6.4 at 304, and 6.1 milliwatts at 314 nanometers. And the epi that I used to publish were these two. So 4.58 at 299, so the 300 nanometer LED, which ended up being 20% efficient in terms of EQE. Sorry, no, this one was 18% efficient in terms of EQE, and 6.14, which ended up being 20% efficient in EQE. The 300 nanometer one was, I believe, 18% in wall plug, and the 6 milliwatt one was 16% in wall plug. So the wall plug efficiency is doesn't correlate to this, because we in the publication, what we did was we just measure the efficiencies with the indium contacts that we use for quick test because of fabrication difficulties. With further polishing of our fabrication process, we will definitely get better voltages, and those wall plugs will meet up better with external quantum efficiencies. So to 20% EQE, so that I was just talking about that. So these quick test powers actually are relatively close to the quick test power that I published in 2023 with the 10% EQE. So the quick test power that I published in 2023 was about 4.4 milliwatts, just as a comparison. So you'd think that that wouldn't give you this 2x increase in efficiency, because the quick test performance was approximately the same. However, what we discovered was that with this thinner n-type aluminum gallium nitride material, our stress state at the top of the LED is different. So as you recall earlier on, when I showed the stress, the compositional gradients, and the stress going from compression into tension, with this thinner n-type aluminum gallium nitride, it doesn't have as much time to go into tension. So the top of the material is at a different stress state, which results in different p-type gallium nitride morphologies. So historically, we've always used this island type formation of p-type gallium nitride to hopefully extract light out between these islands, because p-type gallium nitride is absorbing to ultraviolet light. However, we never really saw that big of a difference in terms of efficiency gains. But in this case, with this recent work, with the different stress state, the islands do not grow in the same way because of the likely more smaller lattice constant at the top of the surface due to less tensile stress in the material. With the small lattice constant, the gallium nitride should nucleate less easily, which results in these smaller islands, which are 10% aerial coverage versus 20 to 40% in our old work. Less than 10 nanometers in height versus 30 to 60 nanometers in height in our old work, and about 1 micron in width versus 2 microns in width. So this gives more room for the light emitted from the LED to escape out the top side, and this is what we believe is the main source of this jump in efficiency that we observe. So this is the UVB LED structure, the world record LED structure that I published. So just show. This is the same structure as before. So this is a test setup that we see with the indium contacts. And in quick test, it was 4.58 milliwatts. What I did was, because of our fabrication issues that we're currently working on, I just took the quick test epi with the indium contacts and wire bonded the indium to a header, and then just mounted it into the integrating sphere to test. And this is the resulting LIV, light current voltage, of these two epi, 300 nanometers and 310 to 315 nanometers. As you can see, it is quite efficient with the EQE. The 300 nanometer LED goes to about 18% peak, and the 310 nanometer LED goes to about 20% peak EQE at under continuous wave operation, so under continuous operation. And at 5% duty cycle pulse operation, we were able to achieve over 25% efficiency on both of these LEDs at 1 milliamp. We weren't able to go to lower current with the pulse measurement because of the limitations of our setup. But I am sure that the efficiencies at these lower currents under pulse operation would be even higher. So these are the numbers to summarize the results. With the 300 nanometer LED, the peak EQE is 18.9%. With 310 nanometer LED, it's 20%. Peak wall plug 300 nanometer LED is around 17%, and 310 nanometer LED is around 15%. These will improve significantly and be closer to the EQE with fabrication. The EQE at 20 amps per centimeter squared, which is a typical higher current density operation for LEDs in industry. So 300 nanometer LED is 8.8% EQE at 20 amps per centimeter squared, and 310 nanometer LED is 10.9% EQE at 20 amps per centimeter squared. So basically what is occurring is that our new material is operating at efficiency similar to the old published material, but at 20 amps per centimeter squared instead of 0.1 amps per centimeter squared. Additionally, the peak pulsed EQE of the 300 nanometer LED is 25.5%, and the 310 nanometer LED peak pulsed EQE is 26.9%. Additionally, I also recently have an accepted manuscript on tunnel junction ultraviolet LEDs. So taking the work with this new optimized LED structure, I optimized a tunnel junction on top of this structure in MOCVD with just a one-pot growth with no regrowth and just everything under MOCVD. So what I discovered was that using low-doped aluminum gallium nitride contact layer instead of just a standard N-type material made it easier for testing because we can sorry, let me get some water. Because the higher doped N-type aluminum gallium nitride that we typically would want as a contact layer would not allow for a quick test. So The quick test works because you can put on an indium on a scribed contact that cuts through all of these layers, and the current will flow through the passive least resistance. And since if all the layers on top of the bottom N cladding are not conductive, then the current will preferably flow through the N-type cladding material. And that's why our quick test works for normal LEDs, because the p-type material is all very non-conductive, relatively speaking, compared to the n-type material. So I replicated that by just initially optimizing on this low silicon doped aluminum gallium nitride, just to get the MOCVD optimization out of the way before changing this back to the highly doped N cladding material. So with this, I was able to do rapid tunnel junction optimization, and I found that using this, our old p-type short period superlattice, and then growing this just to supply some holes, and then growing this very thin 3 nanometer highly doped p-type material at 60% aluminum, and 9 nanometers of highly N-type doped 65% aluminum material. This was able to work as a tunnel junction contact. It is clear that this contact is fully transparent, as there is no p-type gallium nitride in here, and the only p-type aluminum gallium nitride the only aluminum gallium nitride that is lower composition than the emitting wavelength is this 20%, 1 nanometer layer in the p-type short period superlattice, which doesn't absorb much light at all due to the very short, very thin layers, which due to quantum confinement will push the absorbing edge much higher than what the actual band edge is. So what we found was comparing this tunnel junction UVLED to a conventional UVLED, we can see a much greater improvement in light extraction. So over here, what I'm doing is I'm comparing the light output under just a photodiode setup, so just looking at the bottom side emission, versus an integrating sphere setup, which is the solid lines. So the photodiode is the dotted lines, the integrating sphere is the solid lines. Integrating sphere looks at all of the emission from the top and the bottom and sides. And we can see that compared to the bottom emission, our conventional LED with the p-GaN islands increased by our light output by a factor of 1.68. So this is the high light extraction efficiency from the small p-GaN islands that we can see here. But with this fully transparent tunnel junction UV LED, it's even better than this, than the p-GaN islands, with a increased factor of 2.22 times over the photodiode bottom side only measurement. And this comes at a not tiny voltage penalty, but not big at all, at just 1.5 volts at 1 milliamp, or 1 amp per centimeter squared, since our devices are 0.1 millimeter squared. And at higher current densities, this voltage penalty is around 2 volts. So you can see here with the efficiency that we lose the low current efficiency peak due to leakage through the tunnel junction. So these were not actually fabricated. These were quick test devices with indium contacts. So with the scribed indium contacts over here, what happens is some of the current leaks through this top end layer as a parallel pathway to the current that's flowing through the N-type cladding layers. So because of that, we lose this high efficiency peak, but at higher currents, we can see the clear benefit of the fully transparent LED structure with much higher efficiency compared to the conventional p-GaN island LED. And basically, this is just summarizing what I was talking about earlier with the lightly doped n-AlGaN instead of the heavily doped n-AlGaN top contact layer to enable quick test optimization. And we will continue on this work and fabricate fully fabricate tunnel junction LEDs in the near future. And this will definitely result in higher efficiencies compared to these results. So just a summary of my major accomplishments that I presented in this talk. So what I was able to accomplish was reproducible UVLED epi with quick test power greater than 4 milliwatts at 20 amps per centimeter squared at wavelengths between 275 all the way to 320 nanometers in MOCVD. And the results of peak package efficiency of 10.6% EQE and 8.6% wall plug at 285. This was old results from 2023. And with the new results from 2025, we have integrating sphere quick test results of UVLEDs with indium contacts with peak EQE and wall plug of 18.9%, 16.8% at 300, and 20.3% and 15.4% at 310. And these will be improved on with with future work. And we also successfully demonstrated fully transparent n-AlGaN to n-AlGaN tunnel junction UVLEDs at 294 nanometers with 10.4% EQE at 20 amps per centimeter squared efficiency. And thank you very much. And I'm happy to take any questions.
Thank you, Dr. Michael, for this great talk. As you can see, it takes a lot of innovative and hard work to break the world records in this field. And among all these, the work you showed, the one I like most is the way how you connect your integrating sphere to your sample using a quick test indium dots and wire bonding. That will cut the optimization cycle significantly. Yeah. And yeah, I think that contributed to this achievement. It's now, I know it's now midnight in Santa Barbara, so we can have one or two questions from the audience, and then we can conclude. If you have any question, please post it in the chat.